example. Consider a roller coaster with a lift hill of height 25 meters over on the left and a loop height of 18 meters as shown in the figure below. At the top of the lift hill, the roller coaster car has 0 velocity. Then it begins to roll down the hill. Calculate the speed of the car at point P on the loop when the car is 6 meters above the ground. Assume friction is negligible. Okay, so in this case, we've got friction is negligible, so our mechanical energy is going to be constant. Okay, so whatever the mechanical energy is equal to kinetic plus gravitational potential, which is going to be a constant. So whatever we lose in gravitational potential, we are going to gain in kinetic. Now, there's a couple of ways to think about this. At the top up here, there's our roller coaster car. So it's got 0 velocity there. So all of the energy it has at that point is gravitational potential. As it falls, as it gets down to the bottom of the circle, all of that energy has been converted to kinetic. Okay, because we can consider that to be a 0 height. Even though 0 height doesn't mean anything, it's not going any further down. So we can consider that height to be 0. So at the bottom of that loop, all of its gravitational energy has become kinetic. So that's when it will be at its fastest. It then goes back up the loop, and we need to get its speed at point P. Now, there's a couple of ways we could do this. The hard way is to start at the top of the hill, work out its gravitational potential energy, then work out how fast it's going at the bottom, okay, because all of that gravitational potential has been converted to kinetic. So we'll know what its kinetic energy at the bottom is. Then as it goes back up, that kinetic energy is being converted to gravitational potential. Okay, so we can work it out that way. That's the hard one. Let me show you the easy way. Remember, if this is all constant, then remember that our gravitational potential is equal to mg delta h. Okay, so our change in gravitational potential is going to be equal to that. Now remember, whatever we lose in gravitational potential, we gain in kinetic. So our change in gravitational potential is also going to be equal to our change in kinetic. Oops. Does that make sense? Whatever we're losing in gravitational potential, we gain in kinetic. And now all of a sudden, if we look at this, our height change, we don't have to go from 25 to 0, then back up to 6. No. We can look at this as in our height change from here to here. Okay, so from the very top to point P, that's our height change. So we started at 25, we've gone down to 6. It doesn't matter that we've hit 0 first and gone back up, we can still consider our change in height to be 19 meters. Okay, we've just gone from here to there by way of down and up again, but as long as there's no friction, we can do it this way. So our change in height is 19. So our gravitational potential energy, or our change in gravitational potential energy, is going to be the mass of the car. Do we know that? No, we don't. So in that case, we need to be a little bit cute here. So let's go mg delta h is going to be equal to our change in kinetic. All right, all I've done is I've replaced that delta ek with that. And so now, hey, look at that, we don't need mass. Divide both sides by m and the mass cancels out. So now let's rearrange because we want v at that point. So we can do 2g delta h on, square root will give us our change in v. So that is 2 times 9.8 times 19 square root. Anyone has an answer for me, I'd be very grateful. 19.3. 19.3 meters a second. Now, common sense test, does it pass? Well, what I always like to do, I'm not used to dealing in meters per second in my day-to-day life. So I often, if I want to pass a common sense test, I convert that to kilometers per hour. So if we change that to kilometers per hour, we get about 70 kilometers per hour on a roller coaster. That seems reasonable. Okay? Especially if you're, near the bottom of a loop. Seems pretty reasonable to me. So the key with a problem like this is recognizing that mechanical energy is a constant and that your change in gravitational potential energy is equal to your change in kinetic energy. So as we've gone from the top at 25 down to 6, we've lost gravitational, but we have gained kinetic. All right, so as long as we remember that whatever we lose in one, we gain in the other, we can set it out like this. And in fact, in any time you do a problem like this, you can use that formula. mg delta h is equal to delta 1/2 mv squared. All right, if you want to work out, if you've got a change in kinetic to gravitational or vice versa, you can just jump straight to that formula if you like. All right, any questions there? Anything not making sense? Cool. All right, try the next one.